We've been concerned with modeling and describing a system. Now, the next step is, if you have a thorough understanding of that system, we can envision controlling that system in the way we want based on the model. We know how it behaves. We know how the system responds to certain commands, to certain inputs. Now we can introduce a logic to make the system behave the way we want. That's the objective of feedback control. We saw some examples throughout the lectures where we had a simple feedback loop. Most of the time when you have those feedback loops, we are somehow controlling the system. Today you're going to see a extended version of it. Some of you may choose to go down on the robotics path or control systems. So this will serve as the introduction to that. And if you are interested in this type of classes, there are elective courses, there's control systems later on. So let's see the introduction to that today. And the reason it's here is, once again, this is what we did in this class, is the very first step towards controlling something. The first step is to understand how it works before you're able to manipulate it, to control it the way we want. I'll just change the view here. Yep. And again, don't forget to submit the last assignment due today. I have office hours later today. And if later you need office hours to study for the final exam, just send me an email. I don't have any officially scheduled office hours after today. But if you want to meet, just send me an email. I will be happy to schedule a 30-minute session if you would like to. In that case, just make a list of questions and then come with a list of questions that we can go through them. It's a lot better than if you came to me and said, "Oh, Professor, I don't understand systems and simulation." Then what can I do? But if you have a list of questions, we'll address them one by one. And if that's the case, then just send me an email. I'll be happy to schedule a session with you. So by the end of today's lecture, we want to study the concept of feedback control, the introduction to that, define of a proportional integral controller is. Who has heard of PID controllers before? Anybody here? Yeah? Anybody from home? So it seems like it's a fairly new concept. Okay. And then we'll see some practical implementations of a PID controller. So proportional integral derivative controller is one type of controllers that is used to control a system. And this is used at 90% of industrial applications. In any process you see in the industry, we'll see some sort of logic, some sort of feedback control that it takes the model and tries to predict future behaviors of that model for certain inputs, and then adjusts the input to get the desired output. This is one PID controller. It's a box that you can buy from Amazon for like $90, something around that. And as I said, 90% of industrial controllers today use some sort of PID controller. So that's the type of controller we're going to focus on today. There are many others, but this is the most common one. And if you used any sort of robotic system as well, you are likely dealing with a PID controller somewhere. So here is the structure of this PID controller. We have the main portions we had before. We have a process. That's the system we want to control. We have an actuator that provides some sort of energy to that process. The process here is what we've been modeling. For example, a car, a robot arm, an electrical circuit, or anything else. And the actuator is what is providing some sort of, in the case of mechanical system, mechanical energy to the process to make it change state. So in the case of a mass spring damper system, the actuator could be a motor that applies a force to that mass spring damper system. Then you have a sensor that measures the output of the system, and that output is compared with the input. And that's what we do with this summing block here. We are comparing the input and the output, creating an error. And what we did before was to simply take this error, multiply that by a constant, and send that to the plant. So we have a constant here. Let's call that constant Kp. We had that a top loop only. We would take the error, multiply that by a constant, and then make that error times the constant our control action. For control action, what we give to the process is now a function of the difference between the desired output and the current output, multiplied by that again. We're going to introduce now 2 new elements in this controller, and you will understand why they are there and what they do. That's the objective of today's lecture. The first one is a integral part. Let's call this ki. So you're taking the error, multiplying that by ki, and then taking the integral of that over time. That's 1 over s. That's the integral in the frequency domain. What are we doing here? Well, by taking the integral of something, we are looking at what happened in the past. We are taking the integral of all errors over time. What does that do? We'll see that later. So the first one is the proportional part, because it's only proportional to the error. The second one is the integral part, because we are now integrating the error and multiplying that by a constant. And now the control action we give to the plant is a combination of these two. This Kp and Ki are parameters that we can tune and define. And the last element is the derivative part. We are now taking the derivative of the error, multiplying that by a constant, and adding that to the other two. So the proportional gain, because it only looks at the current error, will take action based on the current state of the system. You see, you take an error at a given instant in time, multiply that by Kp, send that to the plant. So the proportional error looks at the current error present in the plant. When you take the integral of something, we are taking the integral in the past, from the time we turn the system on up to the present time. So to some extent, we are looking at the error over time. We are looking at the past error. That's the job of the integral component. And what does the derivative component do? Well, if it is taking the derivative of a system, we are basically looking at its rate of change over time, how it is evolving. And based on that rate of change, we may be able to predict where it's going within a short window, of course. But with that in mind, you can say that we are looking at the future error of the system, because you're looking at how it is changing over time. So we now have these 3 components added together: the present error, the past error, the future error, through the P, I, and D components, proportional, integral, derivative. That's the structure of this popular control scheme. Now let's do what each of these elements here is supposed to do. So we have an error of S. Here we have the control action. I'm going to call that, what did I call it? U of S. So Kp, Ki, Kd gains. One is multiplied by 1 over S, 1 by S. And now we can find the relation between the input and output here. That's just the controller. It's the proportional gain times the error plus the integral of the error plus the derivative of the error. Take the Laplace transform of that. That's the middle equation. And the last equation, you're just factoring out the error in there. So we see all the 3 components, Kp, Ki, and Kd. That's the equation of this controller. Now, if we find, if you calculate this properly, we should have something like S divided by S squared Kd plus Kps plus 1. So this controller is basically adding 2 zeros and 1 pole to the system. Artificially adding zeros and poles to the system to make its behavior the way to make a behavior follow the desired input. Now let's see what each of these elements here do or does. To do that, let's consider this example. We have a mass spring damper system, or simply a mass that is connected to a spring and it lies on a plane with friction. That's the damper there. That's what it's doing, simulating friction between the mass and the plane. And then on the other end of this, we put a DC motor. We are applying a voltage to this motor. The motor will apply a force to the mass. And the objective of our system here is to make the mass move from its current position to x0. We want the mass to go to x0 and stop right there. And we are going to control that through the voltage. We apply a voltage to the motor. We want the mass to be, the spring and the mass to move. So the spring is stretched up to the point where the mass reaches x0 and then it stops. So our first job here is to, of course, model the system to control it. And that's a very good time for a software update. Just give me 1 second. It's updating. Sorry about that. There we go. Hopefully that doesn't mess up my things here. Okay. So our first attempt here, let's do an open loop controller. That is, let's try to understand the system and just reverse that model to control it without the use of any feedback. And then let's add a feedback. So let's create a model for the system first. If we have a mass spring damper system and we are interested in the outputs as if it is the position, we know that the position of this system is the force divided by ms squared plus bs plus k. bk. Are we okay with this equation? We've seen this many times. We know how we got there. Yeah? Okay. Now let's make the assumption that the force applied by this motor onto the mass is proportional to the voltage. In reality, it's a bit more complicated than that. But let's assume that f of s is a constant times the voltage. It's proportional to the voltage. In reality, it's proportional to the current. But well, let's assume that that holds. In steady state, that holds. Which means that the voltage in our system now, the position is alpha v of s divided by ms squared plus bs plus k. If we want this system to reach a position x0, what should be the input of the system now? We are not doing any control, or any feedback control. We are just reversing the model. The question now is, if you want this to move by x0, we have to give this system a voltage step input of a certain magnitude such that the mass will move to x0. The only way to do that is to determine the equation for the system and see how it will respond to that command. If we are dealing with a step input, what would be the final value of this? If we apply a unit step input, for example, to this system, at which position does it settle? When s tends to 0, the limit of s tending to 0 for a step input. So it's the limit. You remember that the limit of s tending to 0 of s times x of s for v of s equals to, let's call this 1 over s. What do we get? We have alpha over k. Vs is 1 over s, right? So we already cancel that. So it's alpha over k. So if you apply a step input, the system goes to alpha over k. That's the first indication. Now let's write our system here in the format, in the block diagram format. We have ms squared plus bs plus k. Here we have the parameter alpha. So we give this a voltage. Voltage is multiplied by alpha gives a force. And the force outputs then the position. What is in this dashed line here is the plant and the controller. We have no control over it. What we can determine is a controller, open loop controller, no feedback, that will now make the mass move to where we want. Let's assume that our desired output here is x0. That's where we want the mass to go. So if you put x0 here, what do we need in the controller such that in the steady state we have x0 on the other side? If this entire thing here in steady state is alpha over k, what goes in the triangle? What goes in the controller in the steady state? K over alpha, the exact opposite, k over alpha. So if you put a k over alpha there, in the steady state, we have the controller, the plant as alpha over k. We multiply them, we get 1. So if you put x0 in the input, x0 appears in the output of the system, actually moves to where we want. We may think, well, we did a pretty good job here. We modeled the system, we inverted the model, and we found what we had to put in the controller. So why do we need to bother about with a feedback control? Well, this only works under 2 assumptions. The first one is that we know the model exactly. We just made an assumption that a force is proportional to voltage, which is not necessarily true. We are also assuming that we know exactly what alpha is, what k is, which may not be the case. Depending on the system, they may vary over time. We are also, so that's the first assumption. We need to know the model exactly. The second assumption that we have here is that there's nothing external to this system acting on it. In other words, there are no disturbances. It will always operate like this, which in reality is not the case. For example, there could be some external forces acting on this mass. If this mass was a car driving on a road, the wind speed would affect how it responds, and that's not part of the model. We have no control over it. The slope of the road would be an external element, also changing the behavior of the system. So this only works if we know the system precisely and there are no external factors acting on it. But this doesn't work in most real life applications. So to compensate for these factors, let's derive a controller. Now for the controller, we are closing the loop, and instead of looking at these absolute values of input and output, we are looking now, taking action based on the error between the desired and the actual output. Let's call this gain here Kp. Here we have the voltage. So we are making the voltage applied to the motor proportional to the error between the desired and the actual position of the mass. And let's see what happens over time now. So with the disproportional controller, we want the system to go to x0. So we could have a desired output here as a step of magnitude x0. This is what we want the system to do. What happened in the beginning when we turn the system on? Well, the system is starting at 0. The system is starting at 0, and we want it to go to x0. The error is x0. And now the voltage we apply to the motor is x0 times Kp. And when that is the case, now the system will start to move. We start to move towards the point we want. So its position that I'm going to plot here in blue will start to increase, and let's assume that this is a underdamped system, overdamped system. We will start to increase like that. And now the error, which is the desired input x0 minus the output, will start to decrease. So the error, if this is the voltage, you can also call this the error. It will start at x0 and we will slowly decrease. Because now the mass is moving towards its final destination. X is increasing, is getting closer to x0, the error is decreasing, which means that the voltage we applied to the motor is also decreasing. That makes sense. The greater the error, the more energy we apply to move the mass towards x0. And as we approach x0, we decrease the voltage, the force slowly. But there is a problem with this approach. The problem is that we can never reach x0. Why? We can never reach x0 in a steady state. Why is that? We're getting closer to x0. The voltage is decreasing because it's proportional to the error, but we will never be able to reach x0. Why is that? Any ideas? What would be the error if the mass is at x0? When the mass reaches x0, the error becomes 0. What is the voltage? 0. And what happens? The mass just moves back because there's a spring pulling it back. Right, so we'll never be able to reach x0 because for a voltage to exist, there must be an error. Otherwise, if the error is 0, there is no voltage. And because there is no voltage, the spring will just make the mass move back. So I'm pulling on the spring, on the mass, holding it very close to the destination I want, but I can never get it exactly at the destination because according to my control logic, once I reach the destination, I would release it and it would go back. All right? So the controller works for an extent, to an extent, because it will now take care of any discrepancies in the model if K is not modeled correctly, if alpha is not modeled correctly, if there are any external forces acting on this body. For example, here, we can add a disturbance. There, an external force acting on it that is coming from, I don't know, from an external factor that is not accounted for in the model. All that is taken into account. The compromise is we'll never reach x0. There is always going to be a steady state error, and this steady state error can never be eliminated. So that's the trade-off. And you may say, well, I like our controller here better because it will go to x0. Well, again, you only go to x0 assuming that we know the model perfectly and there are no external disturbances. So this model here, even though it's not as accurate, in practice is a much better approach. Because you're now looking at the error. So if an error exists, it doesn't matter where that error is coming from. If it's from inaccuracies in the modeling, if it's from the lack or the addition of external forces, it doesn't matter. The controller will take care of it. And we can fix this. We'll see how to fix this. But for a voltage to exist, there must be a steady state error. We can see this. We can prove that the steady state error can never be eliminated, and here is the proof. We can find the closed loop transfer function of this system, and here it is. That's the closed loop transfer function. Sorry. The closed loop transfer function. We multiply that by the desired input, we get the output. Now the desired input minus the output is the error. And you can now calculate the steady state error for a step input. Just set x of t equals to 1 over s. And the result here, for those that are at home, let me just write here because my image is on top of it, is k plus kp alpha. So what we can do with this is look at the result. The result says that this steady state error can never be eliminated. K is a constant that comes from the plant. We can't control it. Alpha is also a constant. The only thing we have here control over is Kp. And given that a Kp must be a positive number, otherwise the system goes unstable, what can we do? Regardless of the value of Kp, positive value of Kp, there is going to be a steady state error. We can never eliminate it. We can make it small by increasing Kp, but we can never eliminate it. Right? And why? Again, because if there is no steady state error, there is no force acting on the mass. Is this clear? Is it clear that the steady state error can never go away in this scenario? And these equations just prove that point. It's telling us now that the greater Kp, the smaller the steady state error, but it can never be eliminated. Careful though, because this Kp is now affecting all the poles of this transfer function. Is affecting the transient. The greater Kp, the more underdamped the system becomes. But as far as the steady state error is concerned, we can never eliminate that. So to eliminate the steady state error, that's where we use the integral component. Now let's add these top line here, top loop here, and let's add a integral gain. Now we have two components. Our voltage given to the motor here is now a sum of its proportional error and integral error times Kp and Ki. That is up to us to find. So let's see what that does. Our job is still the same. That did not change. We want the system to go to x0. Okay, so it's a step input. We want it to go to x0. And as we go to x0, let me just take a quick look at my notes here, how I explain this to myself. Okay. When we go to x0, it's the same. So we are going to start the system, and at the start, the error is very large. The error is x0, is x0 minus 0 is x0. So for the proportional component, it is still the same. Proportional component, let's call this P, is the error times Kp. So we will start at x0 times Kp, and we will start to decrease as we will start to as the mass starts to move. Let me actually make this a bit more clear. Let's put the error here, error of S, and this is Kp times the error of S. So the error will start at x0, and we will start to go lower as the position starts to increase. Same thing as before, exactly the same thing. The proportional error, it starts to decrease. The proportional controller contribution, it starts to decrease. Right? Because you're simply multiplying the error by Kp, and that's the voltage. So this is exactly the same we had before. But now we have this integral component added to it. So what is the integral component doing? Well, the integral component is the integral of the error. So it's actually taking the integral of this area over time. Let's plot it here. How does that look like? Well, it's the integral, so it's just the area under the curve is something that will start to increase slowly like that. The mass is approaching now x0. The error will continue to decrease. The proportional will continue to decrease. And at one point, let's assume that the error reaches 0. Let's call this time when it reaches 0. Let's call that t0. And that's the point. That's exactly the time where the error reaches 0. So let me just try to be consistent here. So it reaches 0, and then it stays at 0. What happens to the proportional controller? Well, it goes to 0. What happens to the integral component? Well, now we are taking the integral of 0, and the integral of 0 is not 0. The integral of 0 is what happened in the past. So that will stay constant at that point. And now notice that we are adding these two, and this is V of S. This is the voltage. So what is happening here is that the motor is applying a voltage that is now held constant by the integral controller. The proportional part is not doing anything anymore, because once we reach x0, the error is 0. The voltage from the proportional part is 0. But the integral is still there. The integral looked at the past error, integrated over the error. When the error reached 0, that integral just becomes constant. It's just the area under it. And that's now what is holding the mass at its final position. So we stretch the mass, we hold it in the actual position we want, and what is holding it there is the integral component. In a steady state, the proportional part does nothing. It helped accelerate the mass towards x0, but once we reached x0, now the integral controller holds it in place. And let's think about it in more detail, because we are always looking at the integral of error. So long as there is an error, the integral will keep increasing. And the integral will only settle once the error reaches 0. Right? Even if we have a very, very small error there, it may take some time for the integral to build up sufficient voltage to make the mass move, but it will. This is to say that if the presence of the integral controller will ensure that the steady state error goes to 0. Always. Always. Yeah. Exactly. Exactly. So we are, when you take the integral of that area, right? And once we reach tau 0, we're just adding 0 to the non-zero area that we just covered, right? So it will always stay constant, and it will start to change again if the error is not 0. Right? Why does the error tend to 0? Right? Why does the error tend to 0? Good. The integral controller is integrating the error over time. And integrating means, in this case, increasing the voltage slowly. And if the voltage is increasing, the mass is moving towards x0. And when it then reaches x0, the error goes to 0, then the integral becomes constant. And then the mass stops. And it stops exactly at x0. Right? So even though now the proportional gain does nothing, the integral controller holds the mass steady. Right? So that's the job of the integral part, is to eliminate steady state error. And it will always do that. Always do that. If your integral gain is too low, it will take some time. You may see the mass jumping, oscillating, and then is slowly moving towards its final destination. That's because the integral gain is too low, so it will take time to build up sufficient voltage to make it move. I'll post a video later that I forgot to do last night that shows that in a real life application. Okay. But that's the job of the integral part. It eliminates the steady state error. Is it clear that so long as there is an integral controller, there is no steady state error? Yeah. Okay. But we solved one problem. We created another one. And the new problem we just made is, look what is happening here. We had this for the initial controller. Now we are adding all this voltage to it. Our controller became much more aggressive. We are injecting a lot more energy into the system, especially in the beginning, compared to only the top. What is the result of that? Overshoot. The system will accelerate too much, potentially, and it will exceed the maximum position before it goes back. So the problem we created here is we eliminated the steady state error, but now we are introducing overshoot potentially. Because the beginning, especially in the beginning there's a lot more energy delivered to the system to make it move. So it will accelerate faster, and it will likely exceed, because of inertia, x0 and oscillate around it before it settles. That's where the derivative gain comes in. I will help with that. Before we go there, let's just prove here mathematically that the steady state error is indeed 0. So we take the transfer function here, the closed loop transfer function. Just find the transfer function of the controller, multiply that by the transfer function of the plant, and then close the loop. That's equation 2. If you do the steady state error for a step input, xd is 1 over s. And when that is the case, we can now have the step input 1 over s minus the entire function times 1 over s. So I factor out 1 over s here. Make the limit of that multiplied by s when s tends to 0. And the result is 0. Always 0. And we see then when s tends to 0, this entire part here goes to 0. And you have the top and the bottom alpha ki. And alpha ki divided by alpha ki is 1. So the system steady state error indeed goes to 0. It goes to 0 for all values of ki. That's another observation we can make here. It doesn't matter what the value of ki is, assuming that it's positive, to not to destabilize the system. If there is a integral component, it will bring the steady state error to 0. How big ki is will now dictate how long it will take for the steady state error to be eliminated. So a high ki will make the steady state error disappear faster, but it will now induce overshoot. And that's where now the integral component, the derivative component, excuse me, will come in handy. because it will try to reduce that. So are we good with the proportional and integral components before we move on? Yeah? Integral component eliminates steady state error. Proportional controller helps the transients, helps it accelerating the system. The greater the proportional controller, the smaller the steady state error. But you can never eliminate the steady state error by itself. And the integral component makes the system always reach the desired position in this case. Okay, so if you're okay with the proportional and the integral, let's move on to the last one, which is the derivative controller. Let's call this KD. Now, what we are doing here is we have the proportional, and now we are adding a derivative component. The derivative component is looking at the rate of change of the error over time. Same scenario again, the mass spring damper system. We are applying a voltage to the motor that is making the mass move. But now we are going to make the voltage proportional to two things. The derivative of the error and the current error. Let's see what that does. Same scenario, we want this to move to x0. And let's create an error here. This is the proportional part. This down here is going to be the derivative part. Let's assume that we had just the proportional part. The proportional part would make the mass accelerate. So the error will start at x0 and decrease slowly. And then proportional controller is simply the error times a constant. So we'll follow the same shape as the error, Kp times the error. What happens to the derivative? Well, the derivative component is now looking at the rate of change of the error. That is to say, it looks at the slope of the error. The slope of the error. And the slope of the error, because the error is decreasing, the slope is negative. All right, the slope is negative. So the error should be a negative value. And then as slowly as the error tends to 0, or sorry, as the error remains constant, it will eventually remains turn to be 0. So what we have here is the error times k, the derivative of the error, excuse me, the derivative of the error times kd. Because we are looking at the rate of change and the error is decreasing. So if the error is decreasing, its derivative is negative. And that's what we see in the derivative component. Now we take the result multiplied by kd. That's the derivative component. So how does that help with overshoots, as I said before? Well, let's look at it, because the voltage is now the sum of these two. Is that plus this one is V of S. In contrast to the integral component, where we added two positive control actions, proportional and integral, and we delivered more energy to the system, here is the opposite. Here we are adding the proportional part to a negative part. We are actually delivering less energy to the system. We are slowing the system down. And why are we slowing the system down? Because we know that the error is decreasing. We are moving towards what we want. We are moving towards the destination. The error is decreasing, so the controller is telling the proportional part to slow down. We are actually going where we want. So we can decrease the control action, and that way we won't overshoot, or we'll reduce the potential for overshoot. If there is overshoot, notice that if there is overshoot, then this reverses, because when there is overshoot, the error goes, let's say, positive and negative. When it oscillates, when it starts to increase again past the overshoot, let's say, let's assume that this was a underdamped system. If it was an underdamped system, it would oscillate, something like that. So the error would oscillate as well, right? Because at some point we went beyond what we wanted. Now the error is positive, the error is negative. If the error is negative, it will eventually come back up here, and during this instance there, the error is now increasing. And if the error starts to increase, then the derivative gain reverses direction, now becomes positive. It is actually adding more energy to the system. So see, if the error is decreasing, the derivative gain is negative, it reduces the amount of voltage applied to the motor in order to slow the system down, to settle at some point. But if the error increases, then it will speed it up to actually take more action to move it towards where we want. And that's why we typically say the derivative gain looks at the future error, because it's actually looking at how fast the error is changing and then taking action accordingly. It's exactly the opposite of the integral gain, which looked at the past error and delivered more energy to the system. Now here, if we are moving towards where we want, it will simply reduce the amount of energy delivered to the system so that we can reach the position without overshoot. Let's see what that does to the steady state error. Before we look at the equations here, what is your feeling? How would the derivative gain influence the steady state error? It's thinking about it. It's looking at the derivative of the error. So what should it do in a steady state? We would increase the error, we will increase the steady state error, we would decrease the steady state error, or we will have no effect on the steady state error. Steady state means constant. No effect. It's the derivative, exactly. It's the derivative of the steady state error. So in a steady state, the derivative there is 0. And if it is 0, the derivative controller should have no effect on the steady state error. And that's precisely what we see in the equations. This is KD. That's the transfer function between the input and output. Same equation we used here to calculate the error for a step input, limit of S of the desired input minus the transfer function times the desired input. That is the 1/S factored out there. We have the result in the calculation, and if we simplify this, I will just rewrite here for those that are at home that my image is on overlapping. There, that's the result. And if you look at the result here, it tells us that the steady state error is only influenced by the proportional gain. That's the only thing that influences the steady state error. It's the same observation, in fact, that we had before. We can increase the proportional gain to reduce the steady state error, but you can never eliminate it. And the derivative controller doesn't show up there. It has no effect on the steady state error. And that makes perfect sense, because in a steady state, the derivative of the error is 0. So it should indeed do nothing. The derivative controller only works in the transient part. So long as the error is changing, the derivative controller does its job. Once the error is steady, then this system, it does absolutely nothing. Okay, so this is these are all the three components. Now all you have to do is to put the 3 of them together. You see that we only used 2 at a time, just to simplify the analysis. But now, excuse me, we can put all of them together. Proportional controller considers the current error and will help with transients, will help with steady state error, will help accelerate the system. Integral gain will consider the past error and therefore eliminate the steady state error. But it will create overshoot because it delivers more energy to the system. And that's the job of the derivative gain, is now to limit these overshoots by anticipating the future error in the system. And now, as designers, our job is to tune these Kp, Ki, and Kd to achieve the performance we want. So this is not a simple task. We have 3 elements to tune. All of them will influence the transient of the system. 2 of them will influence the steady state error. So there isn't a single solution. If I have this specification in terms of settling time or steady state error or overshoot, I have 3 elements to tune now. So it's not as straightforward, and there is no simple solution to that. Right, but that's the idea behind this. We combine these 3 to speed the system up, to eliminate steady state error, and to limit the effect of overshoot caused by the integral control. Any questions? Any questions? No? Okay, so just to make sure that this is actually clear, let's do another example. So we had this mass spring damper system. Now let's do another example here. Now let's see what the proportional integral and derivative components will do. This is a simpler example. We have a car, and you're controlling the speed of the car by pressing on the gas pedal. So we have simply the gas pedal. This is the angle of the gas pedal. We are pressing on it. And we have a system where we give the input is the gas pedal angle. We have a car. And then the output is the speed. Now, here's where we will start to get a bit confused. Do you guys think you drive by controlling the position of the gas pedal or the speed of the gas pedal? Speed, position, position, speed. You actually control the speed of the gas pedal. I'll explain why. A lot of people will disagree with me, and last time I explained this, that caused we went on a long discussion. But here is mathematically why we actually control the speed. So this would be theta dot, and this is theta times s. If okay, we'll get into that. But let's now model the system. The system is the car. That's the box there. So if you're controlling, assuming the speed of the gas pedal, that is to say that once we do nothing, we just press and hold, the speed is constant. Right? The speed of the car is constant. Just press on the gas pedal. That is, if we have a 0 input, means we are at a given position. We're not changing that position. We are holding the position. And then the speed of the car is supposed to stay stable. Right? If we now press slowly, what happens? If you press it slowly, we are changing the speed of the gas pedal, let's say with a sinusoidal waveform, up and down, what happens to the speed? It will oscillate accordingly. What if you press fast, really fast? What happens to the speed of the car? It will not change that much because the car it has inertia, the engine has a response time. So if you press and release fast, you're just making noise, but the speed of the car is not really changing much. So think about the Bode plot then. The Bode plot, this is some sort of Bode plot response. Once the input is slow, the output follows it. Once the input is fast, the output is attenuated. Exactly. Once you increase the frequency, the car has less time to react, so the speed is not going to be affected much. It works exactly like in a Bode plot, where for a certain range of frequencies, we see the output responding. For a higher range of frequencies, the output doesn't respond as much. That's to say that the car could be simply modeled as a pole, a real pole. So let me not call this MS plus B. Let me call this AS plus B. Thinking about a Bode plot, what would this entail? Entailing having one cutoff frequency at a certain point. Past that point, the effects of the input and the output do not affect the car speed that much. So that gives us an idea of how to go about modeling the car. So the input to the car is the gas pedal speed. The output is the speed of the car itself. So here we have the car. We give this theta dot. We get the speed in the output. I'm mixing two notations here. So I'll call this V of t. We take, now we want to control the speed of the car. This is the desired speed. We now have to create a controller logic that will tell us how to control the speed of the throttle in order to control the speed of the car. Let's see what that does. So let's assume, give this example here. We are on a traffic light waiting. The desired speed is 0. And once this traffic light turns green, we want to reach a certain speed and go at that speed. Let's say that's the speed limit. And it wants to go at a desired speed, Vd. So we go from 0 to Vd. What happens to the speed error? We are going from 0 to Vd. As soon as the light turns green, the error will jump to Vd because we are starting from 0. We are at the traffic light. And now, what does that mean? It means that the error theta dot, the speed of the throttle, is to be increased. We are pressing on the throttle. We're pressing on the throttle. The car will start to speed. So we start to move. The speed will start to increase. And as a consequence, the speed of the throttle will start to decrease. And if we reach the desired speed, what happens? We reach the desired speed, the throttle angle is held constant because the speed now is 0. So see, if you're controlling the actual position of the throttle rather than its speed, once you reach the desired speed, what would we do? Just release it, right? But we are actually controlling the speed of the throttle because once you reach the desired speed, you maintain that at a steady position. Does that make sense? More or less, right? Because again, if you want to go at Vd, once you reach Vd, and if you're controlling the position of the throttle, you would just release, because the error is 0. You would just release the throttle, and it would come back, and then the car would slow down. Right? So once the error is 0 and you reach the speed you want, what we do instead is to hold the pedal at a given angle. That means now the position the speed is 0. So that's the idea. But there's a problem with this approach is that the speed will start to increase. And then at one point here, we reach the speed we want. The error is 0. And we are driving at the speed we want. And only then we stop moving the gas pedal if we are driving with the proportional controller in our head. And that's the block C of S. That's how we drive the car. it's too late because the car has inertia. The car has inertia, and well, we'll now overshoot the speed. And if it overshoots the speed, then what do we do? We move the throttle back. The speed of the throttle becomes negative, and then we have to do small adjustments around the speed to maintain that a constant speed. And once we reach the speed we want, we stop moving the throttle. Doesn't mean releasing the throttle, just to stop moving the throttle. Okay. So proportional gain will inevitably lead to some overshoot here, depending on how aggressive you are as a driver, depending on your KP. Does it make more sense now why this is a matter of controlling the speed of the throttle rather than the absolute position? Sort of. But that will lead to overshoot. Because once we realize that we have to stop moving the throttle, the inertia of the car will make it exceed the speed we want. Let's see another example here. Now the job is a bit different. We are going between two traffic lights. We have, and we are controlling the position of the car. What we want to do is to move from the first traffic light once it turns green to the next one that is, let's say, red. And we want to stop right at the next traffic light. And we are once again controlling the speed of the throttle. But now we are controlling the position of the car. So if you're controlling the position of the car, you just need to integrate the speed here. And now our X is the desired position. Y is the actual position. And once the traffic light turns green, we want to go to the next one, which is X0. Which is X0. We want the car to move by X0. So what happens? We are waiting on the traffic light, the light turns green, and we want to advance to the next one, which is red. It's X0 meters ahead. Let's again try to drive with a proportional controller. We are pressing on the throttle, and the speed of the throttle, not the position, is proportional to the error, proportional to how far we are from the traffic light. You already see a problem with this, right? Because we are pressing on based on how far we are on the gas pedal. And we only stop moving the gas pedal once we reach the traffic light. And it's too late. We're going to overshoot. So at the beginning, we want to go to X0. Once the traffic light turns green, our desired position becomes X0. The error becomes X0 as well. And now the car is we are applying full speed on the throttle. The throttle will make the car accelerate. The error will start to decrease. And once we reach the traffic light, that's when we realize, oh, now the error is 0. Good news. Let's stop moving the throttle. But the problem is it's too late, because now the car will go beyond the traffic light because of inertia. We are going to overshoot. The error will become negative, and then the throttle angle is to go, it has to go back, and will oscillate around. We actually have to reverse the car in this example. Reverse the speed to go back to the position we want, and then finally stop at the traffic light. So you can't drive a proportional controller. You would just go to the traffic light, go beyond the traffic light, and then oscillate back and forth up to the point where we stop. So next time you cross a red light, just tell the officer that the problem is that we're driving with a proportional control. And what do you think the officer will tell you? To add the derivative controller. Very good. To add the derivative controller. That way you don't overshoot. Let's see. If we have a derivative gain, we are slowly going towards x0. So the proportional gain is still the same. We'll jump like that and we'll go down. But now if we add a derivative component is telling you slow down. We are actually approaching the traffic light. We are moving towards it. So if you plot the error over time, the derivative of the error, excuse me, it's a negative function. It's 0 and it's negative. And that will eventually lead the car to stop at the traffic light. You just add these two up. And when we are adding these two up, you see here it's a negative value. So you're actually being less aggressive with how much you press on the throttle. You're adding them up, and this is the speed of the throttle angle. And then in the steady state, what is this telling you? Well, in a steady state, if you actually have no steady state error, you are not moving the pedal at all, just holding it at a given position. Okay. In this case here, it will lead to 0. Okay, so the derivative component will help eliminate the steady state error. Now, I mentioned that when we drive, we use the derivative. We control the actual position, speed of the throttle rather than the speed. Let's see if what happens if we control the position directly. So the input to the car is not the speed of the throttle, is actually the position itself. And now the job is a bit different. You have two cars. In the front car, you have a friend who is going at a constant speed v. And we are on a highway or somewhere, and for some reason, we want to drive on the side of that car. It's 0 meters away from it, so just on the side. We want to follow that car exactly. If we are driving with a proportional gain, then what is happening? Well, we are making the throttle angle now proportional to the distance between my car and the car that is moving at a constant speed. What is going to happen is the error will exist at first, and then as I approach the car, the error decreases. And what happens when I reach the other car? Error is 0. What is the throttle position? 0. You're basically releasing the throttle. And then what happens? Then you lose the speed. And then the error will start to increase again because you're falling behind. Then as you fall behind, the controller tells you, oh, no, there is an error, press on the throttle. You press on the throttle, we are moving towards the car. Once you reach the car, the controller tells us, release the throttle. We have no error. And then the cycle repeats. It's the same as the mass spring damper system. We can never reach the actual position of the other car. For an action to take place, there must be an error. For the throttle to be at a position other than 0, you must be behind the other car. Otherwise, you just release the pedal. That's what the controller tells us. How do we fix this? With an integral gain. The integral gain will make such that we are actually considering this area as well. And the integral gain, once we reach 0 here at t0, will slowly increase, and you reach t0, it's constant. So even when the error is 0, the control action is no longer 0. It's basically telling you, just hold the pedal at a constant position, at a non-zero constant position, and that will make you follow the other car with 0 error. That's the idea. Yeah. Okay. Same as the mass spring damper system before. Any questions? No? Okay, so we discussed all these before, but here is a summary with the generic transfer function, the effect of Kp, Ki, and Kd on the transient response. Starting with a steady state error, if you go with a proportional controller, we can never eliminate steady state error. This is just an example of that. We did this again before, but here is another example. Well, let's focus on the transient. How do we find the effects of Ki on the transient, or Kd and Kp? Well, simply find the closed loop transfer function, equate the coefficients to the standard form s squared plus 2 zeta omega n s plus omega n squared, find the damping ratio, and find the natural frequency. With that, we can find the percent overshoot and the settling time. For an integral gain here is the derivation. You can check this later, it's more for information. But this proves our point that the greater the integral gain, the more overshoot there is. Right? We understand physically why, because you're delivering more energy to the system. Here is the mathematical proof of that. If you take that function, calculate the damping ratio, we see that the damping ratio will show up in the Ki will show up in the damping ratio, and therefore the overshoot will be affected by it, and that's what we see there, percent overshoot increasing with the value of Ki. We can do the same for Kd. We know that it has no effect on the steady state error, but we can prove it. And we can prove it here by calculating the steady state error. We'll see that it's independent of Kd. And we also saw that the derivative gains is supposed to decrease the overshoot. So let's do the same analysis again. Take this function, equate that to the standard form of a second order system, find the damping ratio, the settling time as a function of Kd. And if we do that, here is the derivation, we'll see that the damping ratio increases with Kd, and therefore the overshoot decreases with Kd. And so does the settling time. It will decrease as a function of the derivative gain. It may make the system slower in certain aspects, but it will eventually settle faster and will reduce the effects of overshoot. Okay, so here is the summary of that discussion. All the three components, Kp, Ki, and Kd. Overshoot, settling time, and steady state error. The proportional gain increases overshoot, has minimal impact on settling time, decreases the steady state error. The integral gain increases overshoot, increases settling time, and always makes the steady state error 0, regardless of its value. Kd, the derivative gain, decreases overshoot, decreasing the settling time, and has no effect on the steady state error. Okay. That's it. Again, this is the introduction to some sort of control systems, robotics, autonomous systems. If you guys are interested in that, there are some of you will take control systems in the future. This class is the foundation to that. Some of you will go into the robotics stream. And if you are indeed interested in control systems or robotics, here is an elective course that I'll be teaching in the fall 2023. You can sign up for this, and the objective of this class is the extension of this one, but applied to robotics. And it's going to be called the medical robotics because it has applications to medical surgery using robots, but you don't need any biomedical background to take it. So here are some topics you'll see there: robotics, kinematics of robots, how to control them, how to model them, remote operation of robots, how you control a robot remotely using one of these joysticks here, and haptics and haptic devices, how you control, you use these joysticks to control the robot and at the same time feel the forces the robot is doing on the virtual environment or the environment is operating on. And then will be applications to surgical robotics throughout the class. But again, you don't need any biomedical background to take this. We'll use this exact equipment that you see here in the labs. These robot arms are the most precise robot arms in the market today. They have an accuracy of 5 micrometers. And these devices that you see on the left here, on the right, are devices that you basically, it's just a console, you hold it and you can make, for example, the robot mimic what you are doing. You can scale the motion up or down to make it more precise. And then you can control the system in such a way that if the robot touches something as you're controlling it, you'll feel forces acting on your hand as if you were interacting with that object directly. So that's the idea of this elective course. It will be offered in the fall. If you're interested, sign up or send me an email for more information. For those that are more looking for undergraduate research opportunities or are considering grad school later, especially, here's the link to my lab website. What we did in this class is applied pretty much in all aspects of my research, in medical robotics, in robotics in general, in mechanical design, and in electronics, in instrumentation. Pretty much all aspects that you saw here are directly applied to research. Take a look at the lab website if you are interested in part-time research positions, or later, especially later, if you are considering graduate school. Come talk to me at any time, typically a few months before you want to start. And there are opportunities for summer research positions or positions during the regular terms if you want to do part-time, just to see if research is for you or not. I will take 2 minutes, really 2 minutes, to just show you some quick stuff here about the lab. Assuming that I can make this, 1 sec. Where is the, I tried this yesterday. Okay, I don't know how to, that's quite interesting. That should be there. Nope. Okay, anyways, you can see this. Just quickly to give you some more information about research. We are doing robotics for surgery, instrumentation. This is what I was talking about. You see the robots that we are going to use for that class being controlled by that joystick. And what the individual here is doing is simulating kidney stones removal using a phantom kidney and using a robot arm controlled by that joystick. So this is done in collaboration with a company from Toronto. They are interested in this. And that's the project here. It's an industrial project, so it's also a good way to get in touch with the industry partners in the area. So that's the first line of research, robotic surgery. They could work on collaborative human-robot surgery. So the robot does one part of the job, the surgeon does another part. We can do teleoperated surgery. So the robot is in one location, the operator is in a different location, and they communicate. Autonomous systems, the robot does part of the surgery by itself, and image-guided robotic surgery as well. Again, this is purely robotics applied to biomed stuff. You don't need any biomed background. Second area is instrumentation. Here is an example of we are working on with the Ottawa Hospital. These are needles that are instrumented with sensors to measure the tissue body plot, basically, tissue impedance. These needles will inject a current, we measure a voltage, a sinusoidal, and we create a body plot. And based on that body plot of the tissue, we can determine what kind of tissue it is. If it is fat tissue, if it's regular tissue, if it is cancerous tissue, what stage of cancer it is, and so on. So you're using this in collaboration with the Ottawa Hospital to detect, to figure out where the cancer is in certain procedures before they sample it for further analysis. And it's, again, very similar to what we are doing when you looked at body plots. And we can also use this for robotic surgery to make the tools, to steer these tools in the tissue more precisely. Next is the development of those devices themselves. This will be done in collaboration with a company from Montreal called Happily Robotics. What they want to do is develop specific consoles like this one that was developed by one of my students to control surgical robots. These ones that we saw here are general purpose devices. You can control anything with them. The company wants to develop specific ones to control surgical robots. So to make it more safe, to make it more increase dexterity and so on. And can also use this for virtual reality training. There's another project with them that is going on. And some of these will be in your capstone projects if you're interested. And we'll have the chance to work with these robots, ultrasound machines, simulators, lung simulators, for example, surgical tracking systems, virtual reality. Here's a resin 3D printer as well. These devices at the bottom here are tool tracking systems for surgical tools. Okay, so if you are interested, just send me an email and we can talk more about it when the time comes. And with that, we reached the end of 3600. I really hope you enjoyed this class. I hope to see you again in another class in the future. And let me know if anything, if you need any help with anything with regards to this class or beyond. I'm always happy to help if I can. Okay, I'll see you during the final.